Hello everybody! I hope everyone's having a wonderful day. So today I'm going to be proving a so-called generalization. Now in previous video in this series, I talked about the idea of having a property that you prove in a very specific instance, but showed you that how you can take a proof and you can generalize it to say something much more broader. Now I want to show you another example of something like this. And we're going to see how this statement actually connects to two different things we've actually proven before. So this is going to be another property of big O. And I'm going to call this the generalization of the max rule. And we actually seen this so-called max rule before. I'll explain why in a moment. But I'm going to define it for you, and then we're going to prove the claim. Okay? So anyways, so I'm going to imagine I give you some d number of complexity functions. And each one of them is going to be named f0, f1, f2, all the way up to fd minus 1. So there's going to be d of them. I index them from 0 up to d minus 1. And I'm going to have coefficients for these functions. They're going to be named a sub 0, a sub 1, a sub 2, all the way up to a sub d minus 1. These are going to be real values. And what I'm going to do is I want to consider the following statement, and this is what we're going to be trying to prove. So we're going to try proving that the sum from I is equal to 0 to d minus 1 of the product of each one of these coefficients with the corresponding function with, so f sub I of n, or just fi of n, is in fact big O of the maximum among all the functions. So this is just some fancy notation saying, okay, I'm going to index each one of the j values. So I'm going to have j varying from 0 to d minus 1. So I'm going across each one of them. And I'm going to just select the largest of the values among each one of the functions for a given n. And that's what this max function is. This is a generalization of the one that I showed you before, where we only had two functions. So imagine if d was equal to 2. What this would be saying is that it's a sub 0 times f of 0 of n plus a sub 1 times f of 1 of n. Which, if you think of a, so I don't want to spoil it too much, but if you think of the coefficients as 1, you should look a lot like the max rule I proved for you in a previous video. So what we're going to do is we're going to actually prove this claim, and I'm going to show you how to do it. It's actually really surprisingly simple. A lot of the proof's arguments are all going to be relying heavily on the max function. So what do we normally do when we prove claims like this? So what do we do when we normally prove these kind of claims? Well, I normally give you a game plan, right? I tell you what we're going to prove. So we find constants. Constants c, which is a, what is it? It's a positive real number. And n0. What's n0 again? That's a positive integer. Such that for all n greater or equal to n0, what has to be true? I'm going to take these two things, I'm going to write them out in this inequality like this. The sum from I is equal to 0 to d minus 1 of the product a sub I times fi of n is less than or equal to c times the max from 0 to j d minus 1 like this of fj of n. So what I'm going to do is I'm going to select a constant here. Now, before I pick the constant, I want you to really think a little bit about this. Do you remember how I proved the max rule before? So remember when I only had two functions, and I'm just going to ignore these AIs for now. I'm just going to think about when I had two functions, I added them up and I could say, okay, the max of these two things is in fact going to be the max of those two things, right? It's kind of simple. All I'm going to do is think about it this way. If each one of these a sub i's told me how many times I'm going to have an fi of n appear in my sum you'd agree with me that each one of those should be at most the max among all the values of that function. Why? Because it contains fi of n. That's why. So what if I were to take, now remember, these a sub I things, they can all be real numbers, so they may be possibly negative. So what I'm going to do is I'm going to, in fact, take the absolute value of them. So I'm going to add up over them. I'm going to pick C to be the sum from I is equal to 0 to d minus 1 of the absolute value of a sub I. So now what we're going to do is we need to find out what n0 is. Then we find n0 such that for all n greater or equal to n0, the following. The sum from I is equal to 0 to d minus 1 of the product of a sub I times fi of n is less than or equal to the sum. Now I'm going to write in parentheses here just to make it a little easier to see what I'm doing. This is going to be 0 to d minus 1 of the absolute value of that. Remember, that's just going to be C times the max so that's what we're going to need to demonstrate. We need to find out what n0 is. So we need to find n0. So let's figure out what that is. Now, let's proceed. So the big thing we're going to use in this proof is the following observation. And I'm going to come back to this observation later. So I'm going to observe that for all n greater or equal to 1 and 0 is less than or equal to I is less than or equal to d minus 1, both the following, these two statements are true for these two quantities here. So fi of n, now I'm just going right back to what I said earlier. Fi of n is less than or equal to the max among all of the function values for a given n. So we have this, and we also know that this coefficient can never be more than the absolute value of the coefficient. So if you remember something I did before, and I've done this strategy several times, all I'm going to do is, I already know that this bound exists, and I want to bridge between the sum of my function value and these coefficients multiplied. And I want something on this side to allow me to bound by the maximum. Do you see what I'm going to do? What I'm going to do is I'm going to take these two inequalities, I'm going to try summing over them, but I'm going to multiply these two like this. So I'm going to take the products of each respective side, and I'm going to add over them. So I'm going to say, and by summing over all d functions, the sum of the product of a sub I fi of n is less than or equal to the sum of I assigned to be 0 to d minus 1 of the product of the absolute value of a sub I times the max of, this should be like so. So fj of n. So does everybody understand where we got this from? So remember, up here I established that for each one of the I values, it can't be no more than the maximum, right? And that reason is quite straightforward, because remember, fi of n is a part of this computation. So that means that if there's anything larger than it, it's going to be larger. But it cannot be any less than fi of n. Likewise, this is also true because it's either positive, as in it's just going to be equal to this. It's going to be 0, otherwise it's 0, and if it's negative, it's going to turn positive. So I just multiply across these two inequalities, then I sum over all d functions. Now, there's a nice property I have actually with this summation. Would you agree with me that this value right here, this one right here, this guy, so this one right here doesn't change with respect to I. Do you see anything involving I with this value right here for a given n? No, right? It may as well be just some constant, like 2 or something, with respect to the summation. So this would be like if I took 2 times a sub I with absolute value like this, with respect to the summation. So all I'm going to do is I'm going to factor out that from my summation, and you'll see quite quickly that I get what I desired in the first place. So I end up with times the max of fjn, like this. So notice that I have now indeed something that I can assign to be n0. It's up here. It's up here, right? It's n is greater or equal to 1. This is going to hold for all n greater or equal to 1. And I got the inequality that I want to look for, right? Because this right here is c, right? So all I need to do now is I need to pick n0. So I'm going to choose n0 is equal to 1. Therefore, by the definition of big O, what are we going to say? We need to say the results, right? Therefore, by the definition of big O, from the sum from I is equal to 0 to d minus 1 of the product of a sub I times fi of n is indeed big O of the max and we're done. Boom. Isn't that cool? So we proved actually this quite complicated looking statement with very little trickery. And if you were watching some of the older things that we've done in earlier exercises or examples, this strategy I used here should not look very strange to you. I'm going to explain why, because this actually generalizes over 2 things we've actually proven in the past. So the first thing I want to point out to you is, remember, if d is equal to 2, the first thing I want to point out to you is that if d is equal to 2, and you set ai, say a sub 0, a sub 1, all the way up to a sub d minus 1, which is 2, right? This is going to be, in fact, if they're all equal to 1, you'll notice very quickly that this is actually the thing we proved before for the max rule. So we did this actually in a previous video. Now, of course, you can get rid of this 2 part, and now you have a much more general statement for the max rule, where now I have d complexity functions, and now I have a nice simple rule that I can use for any finite number of functions that are complexity functions that I would like to use. So that's one way you can use this. And now this is the one that I would consider the kind of the killer app of this theorem. And so it's because it does 2 different things. It establishes this max rule. It also establishes the second one. So I want you to imagine I give you a complexity function of the form of fi of n is going to be equal to n to the I. And I do this for each one of these values of I, where I've assigned d to be k plus 1. If we try writing this out in terms of that, I want you to see very quickly what happens. So if I'll have a0 times n to the 0 plus a1 times n to the 1, n1, a2 times n squared, all the way up to a sub d minus 1, but what's d minus 1? That's, in fact, a sub k times n to the k. So notice that if you write it out like this should look awfully strange and familiar to you at the same time. First, as a fun technical remark, you'll notice the coefficients are written here in reverse to what we did actually, I believe, before. But the main point I'm getting at is that this is in fact a polynomial. And we actually proved the claim very much like this one before. What did we show? So remember, this is what's now sitting here on this side. So what did I prove at that time about polynomials? That this is in fact going to be big O of n to the k. But what's n to the k? N to the k is in fact when you put I to be exactly equal to d minus 1, which is k. Well, notice that this theorem actually spits out that exact same result at you. In fact, this is a generalization of that theorem. Because notice that when we actually look at when we have this case when I is equal to d minus 1, which is equal to k, notice that that's n to the k, which happens to be right here, which happens to also be the max among all the possible functions for all n greater or equal to 1. So you end up actually getting that result here. I want to show you where exactly in the proof you might recall us using this idea. The fun, and this is kind of the part that I got to disappoint you a little bit, is that a lot of the work in this proof is actually done by the max function. So the max function is doing all the heavy lifting in this proof here. So I'm going to show you where exactly this happens for the polynomial case. So when we have our polynomials, now if you actually go back and look at the proof I did in this case, I relied on the fact that I knew things about different polynomials of different degrees. In fact, if you're kind of curious, d is going to be exactly equal to the degree of the polynomial plus 1. So that's what k is. So that's what k is. It's the degree of the polynomial, and we add 1 to it because we may have a term that actually is just some constant. So where exactly does this all pop in here? Well, okay, so we know that this is going to be in fact less than or equal to k like this. And let's plug in what we have here. So notice that this max function is doing all the heavy lifting. By the way, if you don't know if a function dominates another function for general values of n, you would have to establish this. This is why I did that in that proof. So what I did there was, okay, I have something like, let me take a peek. In my proof, it ends up being something along the lines of n to the k minus 1 is less than or equal to the max across all the, like this, of n to the j, which is in fact equal to n to the k. So we end up with this. Then what we did was, in that proof, we divided both sides by n to the k minus I, right? So this is true if and only if 1 is less than or equal to n to the I. And this is in fact the case for all n greater or equal to 1. So this is actually where in that proof this part pops up. So that's actually where this all comes about. So it's worth noting that you can take a look at how I proved that theorem before, and you can see how this works. And in fact, when I actually did that proof, I did a much more specialized version. This one shows you the technique for which you can do it for any real numbered coefficients. So I'll let you think about that. And this is just something to think about. I'm not trying to prove it formally here for you for the given polynomials. I invite you to go look back at our previous example when we did that. So with that being said, I want to say thank you very much and have yourself a beautiful day. I'll see you later.